We have a point x in Minkowski space, in components x0 to x3, and we've identified this with a Hermitian 2 by 2 matrix, capital X. And now let's consider just some invertible 2 by 2 matrices. So GL2, that's the group of invertible 2 by 2 matrices. It's a group under matrix multiplication. Let's take this X, the capital X, and transform it like this. We multiply with A on the left and A dagger on the right. So since we started with a Hermitian X, this thing here is also Hermitian again, and we can ask, is there a point in Minkowski space, again, such that it corresponds to this matrix? So this means we've done this here. We started with a point in Minkowski space, mapped it to a Hermitian 2 by 2 matrix, and then transformed this Hermitian 2 by 2 matrix with this transformation here above. So we want to see, go this way here and find some map that takes us directly from the x, the little x, down here. So let's call this phi of A times x, some transformation on the x depending on the A. So what would that look like? The phi of A acting on x. Well, first we map x to capital X, our Hermitian matrix, then we multiply with A and A dagger, left and right, and then we go back, last arrow down here, this one, with an F inverse. Okay, so this is the transformation. Now let's check whether this is a Lorentz transformation. So phi of A applied to x, norm squared. What's that? We know it's the determinant of the matrix corresponding to this point here, and that matrix is AX, A dagger. So it's the determinant of AX, A dagger, and that's just the determinant of A mod squared times the determinant of x, and the determinant of x was just norm squared of little x. So in general it's not a Lorentz transformation because of this factor here, but if we make sure that this factor is 1, then we have a Lorentz transformation. And now we consider not arbitrary invertible 2 by 2 matrices, but only 2 by 2 matrices with determinant 1. So that's the group SL2C. Complex 2 by 2 matrices, and the S for special, L for linear, special linear group. Special means determinant 1. And now in that case, we have a factor of 1 here, and we can identify our phi of A with a Lorentz transformation, something in 031. Okay, is this phi actually a homomorphism? Well, let's just check. What's phi of A times phi of B applied to x? Well, that's phi of A times, what was the definition of the phi of B? That was F inverse B f of x B dagger. And now when we apply phi of A to that, we get F inverse of A. And now comes just what we had in here. So that's a B, an F of x, a B dagger, an A dagger. But since B dagger times A dagger is just AB dagger, we really have phi of AB times x. So it is a homomorphism.